Let's now look at calculations of Keq and Q. And let's first start off with calculations of Q. And so let's do an example of this idea. Remember, we have this comparison of K and Q, right? Q, if it's greater than KEQ, we know our equilibrium reaction is shifting left or towards our starting materials. And if Q is less than K, then we have the opposite scenario. While now the equilibrium is shifting right or towards our product. And then if they're equal, well, that just means that we are at equilibrium. So, that's usually when we're talking about Q in calculations is, kind of the question is which way is the equilibrium shifting? Is it shifting left or right, or will this particular material, such as a starting material, increase or decrease, etc.? So the example I'd like to use is hydroiodic acid. So at 721 Kelvin, the KEQ for the formation of HI from hydrogen and iodine gases is 50.5. For basically each of the following, will the pressure of HI increase, decrease, or remain the same? So for part A, we have if 0.01 atmospheres of H2 and I2 are placed in a container with 0.002 atmospheres of HI. So that's our first part A. So I think a good, methodology here is to always have your equilibrium reaction. And if we go back to the text, they're telling us that this is a formation reaction here between HI formed from H2 and I2. So we have our reaction shown here. So hydrogen plus iodine gets you 2 high. Hope you caught that joke. If not, rewind. Definitely chemicals can do that, get you 2 high. So here's one of those. We have a K sub P then equal to our hydroiodic squared, our product, over our pressure of hydrogen and iodine. So that's what K is equal to. And remember, this is also equal to Q. In this case, our Kp is equal to 50.5. And what we want to determine is, well, what is Q equal to? And then how does it compare to our equilibrium constant? So Q is going to equal the same equation, but with the values that we have in terms of the question. So if we go back, right, we have these certain values, right, that are describing our value of Q. So if we plug those in, we would have our 0.002 atmospheres squared over our 0.01 atmospheres for the H2, as well as for the iodine gas. And when we do that calculation, we get a value of 0.04. So if we look at that, we see that, well, Q is less than Kp, right? That means that the equilibrium reaction is shifting to the right or towards product. So that means that our HI pressure will be increasing as a result. So that's the idea of comparing Q to K. You really just want to do the calculation. The equation is exactly the same. It's just a question of whether we're at equilibrium or if we're not at equilibrium. The second one, let's just say if the H2 and I2 remain as 0.01 atmospheres, but the HI gas now has a pressure of 0.2 atmospheres. Right? Again, which way is that equilibrium going to shift? So our Q is remaining the same. We have the same reaction, so we just are really doing the exercise again. And here we have now our new set of Q values. We have the H2 and the I2 remaining the same, but now we have our HI changing, and our equilibrium constant with regards to pressure is not changing, right? It's 50.5. So if we substitute, we have now 0.2 atmospheres squared in the numerator, and then again 0.01 atmospheres for both our starting materials, and here we get a Q equal to 400. So now we find the actual opposite scenario, that Q is now greater than Kp, and so that means our equilibrium is shifting now to the left, or towards our starting material. So in this case, our HI pressure would be decreasing as a result. So that's the nature of Q. Very simple calculation. It's just plugging in the values that are given, and then you take that Q value and compare it to K, and now you can tell whether the reaction is shifting one way or shifting the other, or say whether a certain material is increasing or decreasing in concentration or pressure. All right, let's look now at B, or calculating K sub P and K sub C. So the first thing that we need to kind of address is that, the units for Keq are, very dependent on the equilibrium reaction, and change quite often from one reaction to another. So we are not going to worry about units. In these calculations of Keq. So even going into other Ks, we're just gonna leave out these units because they change all the time. So that's just one caveat in going forward. So let's look at a couple examples, or really a few examples, of calculating K sub C as well as K sub P. But before we get there, we should really talk about, the relationship between the two. And they're interconvertible. There are an equation to relate both of them. So, we can interconvert between the two. And the equation basically brings our gas law kind of idea into the mix. So we have K sub P is equal to Kc times R times T raised to the power of delta N. So our R value here is our gas law constant, the 0.082 liter atmosphere per mole Kelvin. That means our temperature is going to be in Kelvin. And then the delta N that we have at the top is moles of product gas minus moles of starting material gas. And what's really important there is the phase that we're looking at, right? A lot of students just latch on to moles minus moles, but it's a particular phase of those moles. It has to be in the gas phase. So that's the equation. I mean, we can obviously rearrange it and then have our K sub C form as well, which would then just be K sub P over our RT raised to the delta N. So there is our relationship between K sub P and K sub C. So basically, if we know one, we know the other. So let's look at an example of this. We'll start, somewhat easy and get to more difficult ones, and introduce a way to, kind of a method to this process that we will repeat, that will hopefully help us in future problems. So at 300 degrees Celsius, it was found that a mixture at equilibrium for the formation of NH3 from hydrogen and nitrogen gas contained the following concentrations. And so we have a concentration of our H2 equal to 0.15 molar. We have a concentration of our nitrogen equal to 0.25 molar. And we have a equilibrium concentration of our ammonia, which is 0.09 molar. And we want to basically calculate K sub C and K sub P for the following process. So we're looking at nitrogen plus 3 hydrogen in equilibrium with 2 ammonia. So there's our reaction. And we want to calculate K sub C and K sub P. So the first step that we want to do is basically we want to make sure we write our equilibrium reaction. Now here it's actually given to us. We have this right here. So that's fine, but it's not always going to be given. So eventually we're going to have to develop equilibrium reactions on our own. We've done one already. But that's really the first step. So we already have that equilibrium reaction written, which allows us to move to the second step, which is to say, well, what does our, Keq actually equal? And so if we look, our, equilibrium constant would be equal to the ammonia squared over the nitrogen times the cube of the hydrogen. So there's our Keq. And looking at some of the values, we're going to find that really it's probably going to behoove us to start with a K sub C, because they're actually giving us concentrations. But we'll get to that in a second. The third step is to develop our ice table. And our ice table here really stands for, sets of conditions such as initial, change, and equilibrium. And what we have are the important players to the reaction. So in this case, our ice table, we would have nitrogen, hydrogen, and ammonia. And we would have a set of initial conditions, a change, and an equilibrium. So we set up our ice table and basically fill in data from the question. So if we go back to the question, we find that there's really not much information save for what we have at equilibrium. We do have a temperature of 300 degrees Celsius, and then we have our concentrations here, and these are ones that are at equilibrium. So this is a way here to get to our K sub C, since all the values are in terms of molarity. So if we go to our table, what we find is, well, there's not much to fill in for this particular example. There's no information given to us as far as the initial conditions. So that way we don't even have to worry about change, because the equilibrium values are given to us as our nitrogen being the 0.25 molar, right? The hydrogen being 0.15 molar, and the ammonia being 0.09 molar. And so once our ice table is filled out, we substitute into our K and solve. So these are concentrations, so we're going to be starting with our K sub C. And remember, this is equal to our product, the ammonia squared, over our starting material, nitrogen, times the cube of our other starting material, hydrogen. So we have 0.09 for our concentration of NH3. For nitrogen, we have our 0.25 molar. And for hydrogen, 0.15 molar, that quantity cubed. And when we do that calculation, we get a value of 9.6. So that's our K sub C. Pretty straightforward. We just, had the equilibrium concentrations. We plugged them into the equation according to the equilibrium reaction. and we get our K, in this case K sub C. To get to K sub P, right, we would then have to do our equation / conversion. So we would have here our 9.6 for our K sub C. We have our 0.082. We have our 300 degrees Celsius, which would be 573 Kelvin. And then we have 4 moles of gas as, 2 moles of gas as our product, minus 4 moles of gas as our starting material. So our K sub P would just be that 9.6 times 0.082 times 573, right? But that last product we would take to the minus 2 power, and that gives us a value of 4.3 times 10 to the negative third for our K sub P. So that's how we can calculate an equilibrium constant. Pretty straightforward. Since we had equilibrium values, we introduced the idea of the ice table, and now these other examples we're going to start to fill in that ice table a lot more. Let's look at another example where we get more involved with that ice table. So upon heating to 250 degrees Celsius, phosphorus pentachloride gas decomposes according to the following reaction. And so here we have our phosphorus pentachloride decomposing in an equilibrium process to produce phosphorus trichloride and chlorine gases. And so we want to calculate K sub P and K sub C if the initial pressure of the phosphorus pentachloride is 0.686 atmospheres, and that 63% has decomposed at equilibrium. So there's our question. A little bit more to this one, but we want to just kind of keep reinforcing those 4 steps. So the first step is to write our equilibrium reaction, and that's already given to us in terms of the decomposition of the phosphorus pentachloride. And so now we want to discern what is our Keq equal to, and our Keq would be equal to the chlorine times the phosphorus trichloride products in the numerator divided by the concentration or pressure of our phosphorus tetrachloride. So there is our Keq, which takes us to the third step, which is the ice table, and basically fill in with data from the question. So if we look at our ice table, we would have our phosphorus pentachloride. We would have our phosphorus trichloride, right? These are all players within our K and Cl2. And we're going to have that initial, that change, and then that equilibrium. So if we go back to the question and see what we're given, well, we're given a temperature, and that's probably going to help with our conversion value of Kp and K sub C. But we have here an initial pressure of the phosphorus pentachloride equal to 0.686 atmospheres. So that's giving us an initial pressure of one of them, but then that's really it as far as initial sets of conditions. So we have 0.686 atmospheres here, and there's no mention of the products, so we would have to assume that they are 0. We can't bring anything into the question that isn't already there. So there's no mention of the phosphorus trichloride, there's no mention of the chlorine, so they would be 0. We're now going to have a change occur, and what we have to understand about change is, well, change is reflected on, where we need to go. Since there is no product initially, that means product must be formed at equilibrium. This means positive change. The opposite then is true for the starting material. Must be negative change. So what does that mean? That means if we think about this reaction at equilibrium, that we need to produce our products because we start with none of them. And if we're producing the products, that must mean that we are losing our starting material. And the change is going to be based on the stoichiometry that we have. So, since this reaction, if we scroll back, is all 1 to 1 to 1, we can see that in terms of our K in the top right-hand corner. That means that for every 1 molecule of phosphorus pentachloride that goes over to products, right, that would be minus X. And then that would actually form one of our products as well as one of the other product, the phosphorus trichloride and the chlorine gas. And so that's why they're both positive X. So X is equal to change and is dependent on stoichiometry. So there's this idea of change that's occurring. Now, do we have an idea of change? We actually do. We know from the reaction, or the question rather, we know 63% decomposed at equilibrium. So this 63% decomposed, that is getting to the idea of change. So if I were to figure out the actual change, right, then I would say, well, change would be equal to my initial pressure of the phosphorus pentachloride times then the change, which is 63% or 0.63, and we find our change to be equal to 0.32 atmospheres. So that means I would have up top here a minus 0.432 atmospheres. Then I would have plus 0.32 atmospheres for the other X values. And then that produces my equilibrium values. If I take now the initial, I apply the change that needs to occur, I end up with 0.254 atmospheres for my phosphorus pentachloride, and then I end up with 0.32 atmospheres for both of the products. So now you see everything is filled in. And so once ice table is filled out, we can now substitute the equilibrium values, into Keq. So if we start, we have pressures above, so we're going to start with K sub P. And so we would have our 0.432. Let's write the equilibrium reaction or equilibrium equation again. Right, we have our phosphorus trichloride times our chlorine divided by our phosphorus pentachloride. The top left-hand corner, we have those values. 0.432 for our products, 0.254 for our starting material, and we end up with a K sub P equal to 0.734. We can then calculate K sub C by using the other form of our equation conversion. And so here we would have our K in the numerator. Our temperature was 250 or 523 Kelvin. Sorry, I always like to write units for those, at least those two. It's kind of just kind of used to it. And we're taking that whole value basically raised to the first power. We have, back to our reaction, right, we have 2 moles of product gas, 1 mole of starting material gas. So this would be 2 minus 1 in that numerator, or in that raising of the power. So our K sub P would then be equal to this, which is 0.0171. So there's a more ornate equilibrium style question solving for big K. And here we see the ice table filled out a little bit more. And now we have this new idea of change. And so, the kind of the take-home message really with this is that you will always have positive change for a material that initially has 0 as its concentration or pressure. This basically sets up the direction of change for the equilibrium process. So that's really the new take-home message with this idea of change. Is it's just showing us, we're starting with, an equilibrium reaction, but it's not at equilibrium, right? There's going to be a change that occurs, and then we're going to get to equilibrium. So if you think about it initially, we're really talking about Q. And if we don't have any products like we did in this case, that means that we would have to actually make products, right? We have to have some value of K. So that means all of the materials within the equilibrium constant must have a value. So if you start with 0, that means that you always are going to be, undergoing positive change. And then if that's the product side, well, then that means the starting material sides must be negative change, right? It sets up the change for the whole equilibrium process. So that's the big take-home message with this example. So let's do one more example. So here we have a mixture of 0.5 grams of hydrogen gas and 63.45 grams of iodine gas are placed in a sealed 500 milliliter vessel and heated to 703 Kelvin. If at equilibrium, 13.57 grams of the iodine is left, we want to be able to calculate K sub C and K sub P for the following process. So now just kind of, a little bit more intricate. We're not given directly pressures, we're given masses. We have a volume here, so we have a lot more information in this particular question. But the root of it is we still want to calculate K sub P and K sub C, and we're still going to follow our rules. The following process is our 2-high reaction with the H2 producing hydroiodic acid upon combination with iodine. So there's the process that we're looking at. So the first step is again to write our equilibrium reaction, which we've been given. So there's our process. That's now allowing us to set up our Keq, asking, what is that equal to? Well, our K would be equal to the hydroiodic squared divided by the product of the hydrogen and the iodine. So there's our Keq. We then need to develop our ice table, and we need to fill it in. Right, going back to question to figure out what we have to plug in. And so here we have we have our starting materials, our H2, our I2, and our HI. We have the initial set of conditions, our change, and then our equilibrium. So going back to the data in the table, we find that we have some initial conditions. So we see that we have 0.5 grams, 63.45 grams are placed in a 500 milliliter vessel. So here we find initial conditions. And then if we look down a little bit further, we find that we have equilibrium conditions as well. With the 13.57 grams. And we also have our temperature, which is going to help with our K conversion. So we have a bunch of pieces here, but we have to do some work to get them into the proper format for our table. So basically, this step we need to convert mass to moles and then calculate molarity initial, right? That's what we need to do. So if we do those types of calculations, we could start down here with our H2 initial, and that would be taking our mass. We had our 0.5 grams of the H2. Hydrogen roughly weighs 2 grams per mole. So we're canceling out our mass and getting into moles of the hydrogen. And then we're dividing by our volume. Remember, gases take up the entire volume of a vessel. So the volume of the vessel is the actual volume that is used in the calculation of our molarity. And so we end up with a molarity of 0.5 molar. So that is what we're plugging in for its initial concentration. And so now we need to do the same thing for our iodine. The iodine had 63.45 grams of I2. Divide by its molar mass of 253.8. And then also divide by that same volume. So we're doing the same calculation to get the moles, and then dividing by the volume to get the molarity, which we find is actually the same as the hydrogen. It's actually 0.5 molar. If we go back to that question, there was nothing mentioned about initial conditions for the hydroiodic acid, so we would have to assume that there's nothing there, and so that would be 0. If we scroll back just a little bit to look at our reaction, we now know the direction of change. Remember, if start with 0, then you have positive change. And also remember, stoich is important. So if we look at what's 0, well, we have our hydroiodic acid, which is 0. So that means that we would be decreasing in concentration of our starting materials and increasing in concentration of our product to reach equilibrium. And if we look at the equilibrium stoichiometry, we would have minus x, and then plus 2x. Now, the 2x is coming from the fact that there are 2 hydroiodic acids in the equilibrium reaction. So that is where that 2 is coming from, and then the positive direction of change is coming from the fact that we start with nothing of that hydroiodic acid. So now the question is can we figure out the change? And we can, because we know what the equilibrium concentration should actually be for the iodine. Right? If we look back at the question, we do have information about iodine at equilibrium. And it said that there was 13.57 grams of iodine left at equilibrium. So if we do the same calculation as we have directly above, first dividing by our molar mass and then our volume to convert our mass to moles and then moles really to molarity, we get a value of 0.11 molar for our equilibrium concentration of the iodine. So that means that our change would equal the iodine initial minus, right, the actual equilibrium value. Right, because we're trying to figure out what that change is. So we would take our 0.5 molar minus our 0.11 molar, and we find our change to be 0.390 molar. So if we go back to our table, that's what we just solved for in the brackets here for our iodine. And so we're going to see the same type of change for the other starting material, the hydrogen, and then we're going to see 2 times that value for the HI. And so if we calculate those values, we would get also 0.011 molar for the H2, and we get 0.78 molar for the HI. So now we're at step 4. So now with the table filled out, substitute right into our Keq, and we want to solve. So if we refresh our memory here, we were talking about concentration, so we're going to start with K sub C. If we go back to our table, we would find our concentration at equilibrium is 0.78 for the HI. and we had 0.11 for the H2 and the I2, and we end up with a value of 50.28 for our K sub C. We can then now calculate our K sub P, which would be the 50.28 times our R value times our temperature, which is 703 Kelvin, times our delta N raising to that power, and we had 2 moles of product gas and 2 moles of starting material gas. So the fact that that's 0 means that that whole piece is going to really disappear and go to 1. So this whole bracketed area is going to 1 as a result of raising it to the 0 power, and we find that our K sub P in this case is exactly the same as our K sub C. And so that's a more ornate one where we have a lot more calculations involved, a lot more algebra, but those 4 steps are exactly the same. First, write your reaction, write what your K is equal to know what the players are, develop your ice table, fill it in with data. That's oftentimes takes the most time, right? And then once that data is filled in, we can then simply substitute into our equilibrium expression and then solve for our K. So we find that I think is a really good consistent method. So that is calculating K sub C and K sub P utilizing a new idea called the ice table. We'll keep reinforcing this idea and this methodology in the subsequent lecture, where now we get into, what if we're given K and now we need to solve for an equilibrium concentration or an equilibrium pressure. So all these questions, we had an angle to getting at the equilibrium values to solve for K. In the next series, we're going to see the opposite. We have K, and now we're going to get at equilibrium concentrations in the opposite manner. So look for that next.